Okay, so we're going to talk about the relative strengths of acids and bases. You're going to see a chart like this quite often. And the idea here is that the stronger, you can't be both a good acid and a base. You have to be good at one thing or the other, or okay at both. So if you are, the idea is if you are a strong acid, or strong or acid or base, right? So if you're strong at something, you are going to be negligible at the other thing. Negligible at the other thing. So if you're really good at being an acid, you're going to be a terrible base. So negligible, you can't really do anything. If you are a weak acid or base, you are a weak at the other thing. Okay, so when I say, are you a good acid or a base? So an acid molecule is going to always come with a hydrogen. When it interacts with water, an acid molecule is essentially going to give its proton to the water molecule. In fact, the water is a stronger base than the acid because the water just takes the proton. If you are a base molecule, you are going to be able to take a proton from the water. Okay, so the idea here is it's how it deals with water, it's how it hydrolyzes water. It removes a proton or it gives a proton to water. That's what makes something a good acid or a good base. Okay, the stronger it can do that, the better it can do that, the better off it is. And actually, we usually talk about the base, we don't really talk about acid strength much. So here I've got HCl and I've got its conjugate. So this is a list of acids. These are the conjugate bases. So HCl would turn into Cl minus as the conjugate, much like F minus, if that's a base, its conjugate acid is going to be HF. So these are conjugate acid base pairs. So again, these are all really good, strong acids. And therefore, these bases are going to be negligible bases. Okay. On the other side of thing, if I have something that's not very good, it's negligible acid, it actually is going to give rise to a strong base. So those three right there, H peroxide, H minus, and CH3 minus are all very strong bases. And then you're okay at being one thing, you're okay at being the other. So weak acids give rise to weak bases. So if I'm comparing HF to F minus, okay, those two things right there, HF and F minus. HF is actually pretty decent at being an acid, but it's worse at being a base. So HF is an okay acid, it's an okay base, but it's probably a better acid than it is a base. If we look at something like NH4 and NH3, the opposite is true. NH3 is actually pretty decent at being a base because it's further down. NH4 plus is not a very good job at being, does not a very good job at being an acid. So out of these four, which one is the strongest acid? HF and NH3 is the strongest base. The idea being we're never going to get a conjugate acid-base pair that's good at both things. Again, you can only, the idea is a weak acid becomes a weak base becomes a weak acid. Here, a strong acid becomes a negligible base. Just negligible mean it can't actually interact at all. It just kind of hangs out. And a strong base that also becomes negligible, can't interact the same way. Okay. So in an acid-base reaction, we always look at the base to determine which direction is going to be preferred. Okay, so the stronger base is always going to be the reactant. The stronger base is going to do a good job of ripping the proton away from the weaker acid ultimately. So when we have a strong, and so we always kind of look at the bases. Here, this is the base. I'm using blue for bases. This is the base, and so is this. Those two are the bases. The other two things are acids. Okay. So which of these two is a stronger base, H2O or Cl minus? Well, let's look at our list. H2O, Cl minus. H2O is in fact the stronger base. So that means that this direction is preferred because we want the stronger base to be the reactant. In fact, it is so much preferred that there is zero return trip. It is never going to reach an equilibrium. The equilibrium lies entirely to the right because H2O is a much stronger base than the Cl minus. That's for strong acid because the kind of negligible base, right? This is not a base actually. Although I did call it a base, it's not really, it's negligible. It's actually not even gonna be good enough to be considered a base. But when we have a weak acid base combo, a weak acid and base pair, so here I have, this is my acid, meaning the H2O is my base. Now, because this reaction is going in two directions, if we look, we'll notice that, well, here's my acid and this is my base. Again, we have this conjugate acid-base pair, conjugate acid-base pair. But what we're going to focus on, the two bases. So H2O and CH3CO minus. So looking at these, that is my first base and water is my second, which is the stronger base, the CH3COO minus. Just a quick aside, that is acetate. Acetate is the stronger base. Because acetate is the stronger base, we're going to see a preference in the direction of that as the reactant. So this is an equilibrium. The preference does go away from the stronger base, so the reactant is a stronger base, but because they are weak, we will see a small return in that direction. So we do have an equilibrium, but this lies with the left, as in this is reactant favored. You would not see much reaction when we combine these two things. Okay, good. Yeah, so reactant favored for our equilibrium. Next up, which of the direction will the following proceed? Again, what we need to do is I need to find the acids and the bases, the stronger acid. So let's say it lies to the right. I'm going to erase these, but the idea is if it lies to the right, we would say, all right, well, this is what the equilibrium looks like. Unless it produces something negligible, then we would lose that arrow, right? So decide which direction is preferred. And I want to point out the fact that when you have something like this, let's break it into its ions, because the anion is usually the base. So we want to ignore any of the cations, especially group 1. They kind of get in the way and they make things look confusing. So here I have Na2CO3. So I have I have two Na pluses, and I have CO3 2 minus. CO3 2 minus, CO3 2 minus. That's really the thing that I'm looking at here. Plus CH3 COOH. I'm not going to balance this. We don't need to. And then the same thing for the other one. If I get rid of the sodium, I end up with that. All of these are aqueous. I don't really need to add that. And then H2CO3. So you're never going to find something with sodium or group 1 on the, you're going to only find anions or cations on those strength tables. So there you go. So I'm going to move back to the top. So if you've got this written down, I'm going to move back to the top. If you don't have this, if you're taking notes, you can pause it. So yeah, so basically tell me which direction those things prefer. And pause it now, make that decision, and I'm actually going to walk through it right now. Okay. All right, so here we're going to decide which. I'm going to highlight the bases. NH3 is the base on the left, and F minus is the base on the right. So NH3 and F minus. NH3, F minus. NH3 is the stronger base. They're both weak, meaning the direction is toward away from NH3. So the preference is to from left to right with a small return because they're both weak. And now bases for the other side. This is the base. I use different color. There's one base. There's another. Always look for anions. Anions are bases. So CO3 2 minus, CO3 2 minus, and what was the other one? Acetate. Acetate being the base. CO3 2 minus is the stronger base, meaning this one also is going to prefer that as in that direction. There we go. Both of those are weak, so it is going to be in equilibrium. Both of these are reactant favored. Both of those are going to have more of the reactant than the product. Okay, good. So that's the idea behind strengths of acids and bases. These tables are important. Remember, strong acid, negligible base, weak acid, weak base, weak acid, strong base, negligible acid. Okay, so weak and weak line up, strong and negligible line up. So let's talk about the idea of the autoionization of water. So water molecules are neutral, and they don't really, what they end up doing is pure water molecules, you have just water, and actually one of the water molecules as a liquid can interact with another water molecule as a liquid, and it creates this equilibrium where you actually have one acting as an acid, the other one acting as a base. So what you end up with is that first water molecule will grab a proton from another water molecule and OH minus. So ultimately what you have is this has lost, or I guess gained in this case, plus H plus. This has minus H plus, meaning if that gained H plus, this is going to act as the base. This is acting as the acid. And we have these two new species, both in aqueous. So the autoionization, they ionize each other. But we never really have the water molecules present. A better way to, not really a better way, but maybe a more obvious way to look at it is if I have liquid water is in equilibrium, it actually just ionizes by itself into H plus and OH minus. And this is kind of the standard that we start with. So here's the idea. Water ionizes itself. And you'll see why it's important in just a second. So we have water that ionizes itself. So let's draw an equilibrium expression for this. So we're going to call this Kw, which is the ion product constant of water. And Kw at 25 degrees is 1 times 10 to the negative 14. Kw is equal to, well, this is just an equilibrium expression. So we know how to do equilibrium expressions. Concentration of products over concentration of reactants. The reactants are liquid, so we actually are not going to include those. That's it. This is the ion product of water, 1 times 10 to the negative 14. This is an important equation, so you should know this one. This does get provided, I believe, but you should know this. And there's a very important reason you need to know this, and we're going to walk through it in just a second. But so this is what we have, right? By the way, this is a constant that we're going to use, but this only occurs at 25 degrees Celsius. This is only true at 25 degrees Celsius. What happens to Kw if we change the temperature? Well, if we change the temperature, so first of all, we should say that this process, H2O liquid, autoionizing into H plus and OH minus, both aqueous, okay? This is an endothermic process. So delta H is positive, so it's greater than 0, meaning it's positive, okay? So if it's positive, that means we have heat as a reactant. Having heat as a reactant, because it is in fact endothermic. What happens if I increase the temperature? Remember, this is Le Chatelier's principle. If I increase the temperature, that means there's an increase in heat, quote, heat. By increasing the heat, we are seeing a shift away from the addition. Ooh, shift, there we go. Shift away from the addition. So we are going to shift it to the right. So by increasing heat, by increasing this, we need to shift away from it. So that means that I'm going to see an increase in the concentration of H plus and increase in the concentration of OH minus. So an increase in the concentration of products. What does that ultimately mean? What that means is by increasing, adding H plus actually leads to a decrease in pH. Warmer water is in fact more acidic by definition. Yeah, a little weird, but we see a decrease in pH because we are increasing the concentration of H plus. Okay. So let's talk about pH and pOH. Okay, so yeah, let's talk about the idea of pH and pOH. In fact, I'm going to talk about pH and pOH next. So we can stop that right there.